What is a garbage collector? In C, we've been manually managing our memory, which is not only difficult to do, but tricky to say. I always feel like I'm going to make a big mistake while I'm talking about it. However, that's not the only strategy for managing memory. There are alternatives like the Rust strategy, which uses a borrow checker, which, while still including sort of manually managing the memory, truly, the Rust compiler is the one that determines whether an object's lifetime is complete or not, and if so, it will free that object. However, a garbage collector is quite different. In garbage collection, the language itself, for example, Python or JavaScript or Go, determines if a particular object or value is still live. Live means that the value could possibly be useful. If we had a variable that was created inside of a function, and then the function returns without referencing that variable anymore, we want to give that data, that memory space, back to the operating system. In that case, we would consider that object no longer live, right? Because there's nothing that could possibly reference it. It's useless. And in garbage collected languages, it will figure that out automatically for you. However, it's not free. The garbage collector still has to use some algorithm to determine what values are still alive or not. And like many other languages, for example, in Python, a lot of Python is written in C, or at least one implementation of it is in CPython. That garbage collector may be written in a different language. So let's talk about some of the algorithms that are useful for garbage collectors to determine whether a particular value is still live. The first kind is called reference counting. Reference counting is probably the simplest version of garbage collection. And what it is that every object has an additional field that is its count. And when you create the object or some other variable references the object, consider something like a list. If I have a variable foo and I put it inside of a list, okay, well now the reference count for foo might be 2 because it's one for itself and then one for this list. Now, when we remove that list, or maybe we pop that element out of the list, we're going to drop its reference count by 1. And maybe if we return from the function that created foo, now its reference count might drop to 0. Once an object's reference count drops to 0, then we give that memory back to the operating system. Naive reference counting has some downsides, like an inability to track cycles, and it is quite expensive because every time we do an operation, we have to go modify all of the objects that we're touching. Because of that, people thought of other strategies. The other primary one that we're going to cover is mark and sweep. Mark and sweep is an idea that we'll be able to find all of the variables that are directly referenced by our stack frames, generally speaking, and then we will trace through all of the connections of those variables to find any other ones that are referenced by the roots. Once we've done that, we'll be able to determine, aha, I see all of the set of variables that are directly referenced and indirectly referenced, so any of the variables that are not marked, we can sweep those away. Really, the sweep is actually the search, but I kind of like to imagine that you sweeping them back to the operating system. Mark and sweep is a bit more complex, but it can handle certain cases that at least naive reference counting can't handle, like a list who references another list who references back to the original list, which, see, that's a cycle. That's a problem for reference counting. You'll never get down to 0, but for mark and sweep, if none of the roots touch either of those lists, we'll be safe to mark them as not alive and free them and give them back to the operating system. Additionally, mark and sweep doesn't require us to do operations every single time that we touch or reference a variable. We only have to do the work when we do something often referred to as a GC pause, a garbage collector pause, where the garbage collector is going to do some work to go check which variables are still alive. One of the key things that I'm trying to emphasize here is that garbage collection is not free. There will always be some work for the language runtime to determine, is this particular value still alive or not? In languages like C, the programmer has to do that ahead of time and hopefully remembers to do it correctly. Or in Rust, maybe the compiler does some checking for you to let you know that. But in garbage collecting languages, you pay that expense at runtime rather during development time. That's one of the trade-offs you have to decide when picking a language, is where do you want to pay that cost?